All right, we are back to inverse trig functions. We saw in the past, like 2 weeks ago, that there are restrictions on the domain of our, oh my goodness, on our inverse functions. And here's why. Well, in the first quadrant, all trig functions are positive. Okay, second quadrant, sine and its reciprocal cosecant. Third quadrant, tangent and its reciprocal cotangent, and then fourth quadrant, cosine and its reciprocal secant. Okay, and mathematicians decided that, okay, if I'm looking for inverse sine, right, and its positive ratio, I'm in the first and the second quadrant. We need there to be one and only one solution, so we're restricting its domain. It also has to do with, if you saw, hopefully all of us did, the video notes from a couple weeks ago when we were graphing the inverses. In order for our inverse to be a function when graphed, its inverse, right? So cosecant. In order for cosecant to be a function, inverse sine. What? Inverse sine. Then its inverse had to be 1-to-1, and sine isn't. So we restricted the domain, and that has to do with the reasoning behind this as well. So if we look at our first example, inverse tangent of 1/2. Okay, well, that's not coming from a special right triangle, our 30, 60, 90, or the 45, 45, 90. So we need to figure out where theta is located. We need to know what triangle this is coming from so we can then find the sine of theta. Tangent is, if we remember, between negative pi over 2 and pi over 2. And the reason that it is not an equal to is because it's, very good, there are asymptotes at pi over 2 and negative pi over 2. So we say that it's from negative pi over 2 to pi over 2 non-inclusive. Okay, so if inverse tangent of 1/2, that's positive, so we're in the first quadrant. I'm going to extend out on the positive x-axis, up on the positive y, and back to the origin where our reference angle is located. Tangent is opposite over adjacent, and then because we have a right triangle, we can use the Pythagorean theorem to figure out what our hypotenuse is. And in this case, the hypotenuse is rad 5. So then the sine is opposite over hypotenuse, and we have to rationalize because we can't have a radical in the denominator. So sine of theta is rad 5 over 5. Nice. Okay, the next one is inverse sine. Okay, inverse sine we saw was just like tangent, except it can be equal to pi over 2 and negative pi over 2. So inclusive, negative pi over 2 to pi over 2 inclusive. Nice. All right, well, again, there isn't a special right triangle that has a sine value of 1/3. So we need to find where this triangle is located and just calculate the cosine of theta. Since let's keep my colors going. There we go. Since sine is negative, we're in the fourth quadrant. So we extend out to the positive x-axis, down to the negative y, and back to the origin, where our reference angle is located. Now, sine is opposite over hypotenuse, and the hypotenuse is distance between the ending point and the origin. So the hypotenuse is never, ever, ever going to be negative. We can use our Pythagorean theorem to figure out what that missing piece is because it is a right triangle. Let me finish writing this out real quick. So we get that x squared is 8, so that missing piece is 2 rad 2. And that is positive because we're in the fourth quadrant, so that's the positive x-axis piece. So cosine is adjacent over hypotenuse, and there we are. Sweet. All right, last but not least is cosine. Now, inverse cosine is a little bit different. Inverse cosine is between 0 and pi, okay, because in the first and second quadrants, cosine is positive and then negative. So in interval notation, it looks like this. There we go. So, oh man, yep, one more that we don't have for our special right triangles. Don't stress out about that. I know our unit circle is really helpful. It's really nice when we can just pull out that measurement. But if we don't, just go to your triangles, okay, build it, figure it out from there. Totally fine. So inverse cosine is negative. So we're in the second quadrant. We extend out to the negative x-axis, up to the positive y, back down to the origin where our reference angle is. So cosine is adjacent over hypotenuse. Again, if we're in the second quadrant, The x-axis is the negative, not the hypotenuse. And then we can use the Pythagorean theorem to figure out what that missing leg is. I keep writing plus, it's such a habit. There we go. So y squared is 8, which means it is just like we saw in the previous example, 2 rad 2. Okay, so then tangent is opposite over adjacent with our given triangle, which means it's negative 2 rad 2. Sweet. So that should be a review. Hopefully it refreshed your memory on a few things. Let's get to graphing. We are going to graph the reciprocal inverses. Okay, so let's remember cosecant. Cosecant is the reciprocal of sine. And for cosecant and secant, we would always sketch their reciprocals. And I'll show you why in a second. Let me label my x-axis. Okay, so at 0, sine is 0, and so forth. And the reason why we did this was, especially when we had transformations, because if we're dealing with reciprocals, and sine is 0 at 0 radians, right? What is the reciprocal of that? Yeah, it's undefined. So it helps us to find where the asymptotes occur. Okay, so for cosecant, there's an asymptote at the y-axis, at pi. It's wherever it intersects the midline, but when we get to shifting vertically, we don't always have that luxury of seeing the x-axis, right? It's the midline. And then the maxes and the minimums, and then it extends up or extends down depending on whether it's coming from a max or a min, making sure not to intersect the vertical asymptote because that is where our function's undefined, but merely getting really, really close to it. Okay, so is cosecant 1 to 1? In other words, for every x, is there one and only one corresponding y? And then for every y, is there one and only one corresponding x? And the answer is no. Okay, and since our answer is no, we do have to restrict the domain because, as I mentioned earlier, if a function is not 1 to 1, its inverse will not be a function because the x and y values switch. So if it's a function, that means the x's don't repeat. But if it's not a 1 to 1 function, that means the y values repeat. So when we graph the inverses and the domain and range values switch, the x and y switch, it then becomes not a function. Okay, so that's the reasoning behind all of it. Whew, a lot of words, I know, but it's really important. So we're going to restrict the domain of cosecant to be exactly the same as its reciprocal. We're going to restrict it to be from negative pi over 2 to pi over 2 inclusive. What does that look like? Well, we're going to go from negative pi over 2 and include the asymptote to pi over 2. Those are the only pieces that we'll be graphing. Okay, so what does the function look like? It looks like f of x is equal to cosecant inverse of x. Don't forget the negative 1 exponent. And now our x and y values switch because these are the inverses. So our x values go from negative 1 to 1. And then our y values assume the radian measure. Okay, well, there is an asymptote at the y-axis, which means there is now an asymptote at the x-axis. And there's 2 points that I see. For the function of cosecant of x, I see a coordinate at negative pi over 2, 1, and pi over 2, 1. So that means for the inverse, they switch. We're going to have a coordinate at negative 1, negative pi over 2, and then 1 pi over 2. So negative 1, negative pi over 2, and 1 pi over 2. And you'll notice that they are curving towards their asymptotes. Well, which direction do we go? If we go this way, oh, yep, they're going to cross. Therefore, it would not be a function. Make sure you always check that. Okay, really important. So we're going to curve to the right and to the left. So they curve away from each other. Now, for transformation, pieces, we'll say, if there's a horizontal, these are the only 2 points. If there's a horizontal stretch or compression, you're affecting your x values. Yeah, you're just going to move them further away or closer together. If there is a vertical stretch or compression, you're moving up or down from each other. Okay, that's not going to change. And these are the only 2 points that I want you guys graphing. Also, if there's a vertical shift, that moves our horizontal asymptote. That's it. Easy. All right. Okay, so our domain goes from negative infinity to, -1 inclusive, jumps over to 1 inclusive to infinity. The range goes from negative pi over 2 to 0, and then 0 to pi over 2. We're not using a bracket on 0 because that's where our asymptote is. We don't exist there. Okay, just so you guys know, your book's going to state it like this, as negative pi over 2 to pi over 2, because that's the domain of its inverse, and then it's going to state the inclusion, or the exclusion, that y cannot be 0. Okay, just so you're comfortable with both and seeing both. Sweet. Okay, so there's inverse cosecant, which means that we now get inverse secant. Secant is the reciprocal of cosine, so the x is still in radians, and the y still goes from -1 to 1. Similar for cosecant, we're going to sketch its reciprocal. We're going to sketch cosine. And why? So that we can see where those asymptotes occur. Again, since there's no vertical shift, it's going to be really nice because they're at the x-axis. They're just at the midline. La la la. Okay, sweet. So it's at the midline because the midline is where the value is 0. Okay, so that's where we're going to have those undefined moments. Because if I take the reciprocal of 0, I am now dividing by 0, and I can't do that. And then, of course, at our maxes and our minimums, we're going to have points, and it either extends up, not intersecting or crossing that vertical asymptote, because that is where the function is undefined, or down. Now, is secant 1 to 1? No, it is not. Okay, so since we said no, we have to restrict the domain. Otherwise, its inverse will not be a function. We can't have that. So we're going to restrict the domain the same as its reciprocal. We're going to say that it goes from 0 to pi, inclusive. Which means that I'm going to start at 0. I'm going to graph that piece. I'm going to graph this asymptote. And then I'm going to graph that piece, 0 to pi. All right, so what does that look like? We're going to find out. Okay, so the inverse means that f of x is equal to the inverse secant of x. Remember, it has that -1 exponent. And again, our x and y values are switching because we're graphing inverses. So my x-axis goes from -1 to 1, and my y-axis I only care about from 0 to pi. Okay, so we do have an asymptote at x equals pi over 2, which means y equals pi over 2 for the inverse. And on the secant of x function, I have a coordinate at 0, 1, and pi -1, which means for its inverse function, there's a coordinate at 1, 0, and -1, pi. Yep, the only function points that I want you to graph. 1, 0, and -1 pi. These are also, as you can see from the secant function, they are also extending towards the asymptote. It should be extending away, but think about if you were to accidentally graph them this way. What's going to happen? Yes, they are ultimately going to cross each other, eliminating all possibilities of this actually being a function. So we're going to draw it towards the asymptote, but away from each other. If you have any horizontal stretches or compression, just like we saw from the previous function of cosecant inverse, it's going to take these values and stretch them away from each other or get closer. A vertical shift will shift the horizontal asymptote. Yes, you should be writing this down if you're a forgetful human. And then if we have any sort of horizontal shift, it shifts the x coordinates. Any vertical shift or horizontal stretch or compression, it also affects those. So the transformations don't change. We've seen that. That's nice to have that comfort in knowing we know how to do that. Okay, domain. Domain goes from negative infinity to -1, inclusive union, inclusive 1 to infinity. Inclusive, reminder, just means that it's the brackets because it's a closed point. The range is going to go from 1 to pi over 2 because that's where the asymptote is. And then it's going to go up. Oh my gosh, 0, 0. Come on, Patterson. To pi. I'm like, that doesn't look right. What's wrong? Okay, and then your book is going to go from 0 to pi with the exclusion that y can't be pi over 2. Okay, of course, we prefer the interval notation, but I want you to be comfortable with what the book is listing out as well. Yes, I really only want you to graph the 2 points in the asymptote. You'll be okay. All right, so we did cosecant inverse. We did secant inverse. What's left? Cotangent inverse. Okay, so cotangent, our y-axis is still going to go up to 1 and -1. Let's do pi over 4 here, and then pi over 2 and pi. Did I say cotangent inverse? I meant cotangent. We're not at the inverse yet. Slow down. Okay, and we approach cotangent a little bit differently. We don't actually graph tangent. It's reciprocal. We just think about the coordinates. So the tangent of 0 is 0. So that means its reciprocal would have an asymptote. Same with at pi and -pi. And the tangent of pi over 4 is 1, which means the cotangent is also 1. And so that's how we originally graphed cotangent. Okay, a different approach for sure than the other two. We didn't sketch its reciprocal, but we did think about their points and what would happen when we take the reciprocal of them. Okay, so is cotangent 1 to 1? Of course not. Okay, so since we're answering no, yes, we have to restrict the domain so that it can be 1 to 1. Otherwise, its inverse will not be a function. Okay, now this is the one exception. We could cut it in half so that we get the tiny little pieces like that, but mathematicians chose not to. They chose to restrict it from 0 to pi, and in looking at the cotangent function, that makes sense because you have an asymptote at 0, and then if you go all the way to pi, you get that beautiful curve, and then you get another asymptote for closure. Okay, so that's what we're going to do for cotangent. And let's go ahead and write the coordinates down because it splits paper so that we can see it. The asymptote is at the x-axis, or sorry, the y-axis, which will be the x-axis. So we have a vertical asymptote at x equals 0 and x equals pi. And then the coordinates that we have are pi over 4, comma 1, pi over 2, comma 0, and then 3 pi over 4, -1. Okay, the reason I'm doing that is because when I scroll, we won't be able to see it very well. All right, so the inverse, what does that look like? In function notation, I'm going to go ahead and switch my color. It's f of x is equal to cotangent inverse of x. Remember, -1, it's important. Okay, and our x values, right, go from 0 to pi, which means that that is where our y values are going to go. Pi over 2 and pi, and then our y values go from -1 to 1, which, since this is the inverse, is where our x values are going to go. Okay, vertical asymptotes become horizontal asymptotes. So we have a horizontal asymptote at y equals 0 and y equals pi. For the inverse, I'm going to have a coordinate at 1, pi over 4, at 0, pi over 2, and at -1, I'll just erase it. I know I have that capability. 3 pi over 4. So we have a coordinate at 1, pi over 4, 0, pi over 2, and -1, 3 pi over 4. And it is going to curve just like that. and there is inverse cotangent. Pretty awesome, right? So these are the 3 points that you'll use for transforming, okay? The domain is all real numbers, which is the inverse of the cotangent range. Very good, because inverses switch their domain and ranges. Okay, the range is going to go from 0 to pi non-inclusive. Great, nice job, you guys. Okay, so there's your inverses. You now have, holy moly, 3, 6, 9, 12 graphs. Sine, cosine, tangent. Cosecant, secant, cotangent. Inverse sine, inverse cosine, inverse tangent. Inverse cosecant, inverse secant, and inverse cotangent. Oh, man, your friends are going to be jealous. Okay, so we just have a few more examples to go through just to make sure that we do understand the concept of inverses. Okay, so inverse cosecant of 2. Remember, cosecant is the reciprocal, so you can approach these by applying the reciprocal. Inverse sine of 1/2. And we know that it's positive, so we're in the first quadrant. We also know that sine of pi over 6 is 1/2. Okay, feel free, if you're not comfortable with reciprocal values, to take the reciprocal. Inverse secant of 2, which means we're looking for the inverse cosine of 1/2. Again, it's positive. We're in the first quadrant, and we know that the cosine of pi over 3 is 1/2. Okay, what about cotangent, though? So cotangent of negative rad 3. Remember, inverse cotangent is between 0 and, yes, pi, so we got to be careful. Okay, so we're looking for the inverse tangent of negative rad 3 over 3. Tangent of pi over 6, good, is rad 3 over 3. And we are not in the fourth quadrant for tangent. No, no, no. Think about between 0 and pi. So if it is pi over 6, that means that it is 5 pi over 6. Cotangent's the only one you have to be a little bit careful of, okay? Inverse cotangent, I'm going to write this out for those of us that need to see it, okay, of negative 1 means we're looking for the inverse tangent of negative 1. Normally I would say this is negative pi over 4 because that's where tangent is restricted, an inverse tangent. But it's cotangent what we're looking for. So that's a pi over 4. That's a 45-degree reference angle, which means that this is going to be 3 pi over 4, okay? You can go back and apply the reciprocal, that such as we did for A, B, C, and D, but be careful if it is inverse cotangent, okay? Because inverse cotangent and inverse tangent are not restricted in the same location. All right, last but not least, oh, remember these? I know we did these in our homework also, but I want to make sure you guys truly understand what's going on. So tangent, inverse tangent of U, okay? We have to find where this triangle is located. Doesn't matter what theta is, where is it located? Well, it's positive. So I'm going to be in the first quadrant. The triangle looks like this with theta at the reference, or our reference angle theta at the origin. Whew, that was rough. Okay, so tangent is opposite over adjacent. We're going to use our Pythagorean theorem to figure out what the hypotenuse is. So it is the square root of u squared plus 1, which means that sine is opposite over hypotenuse. If we want to rationalize, multiply by the denominator. So we get u times the square root of u squared plus 1 all over u squared plus 1. I'll take either answer. Don't want to rationalize? Don't. These get a little wicked. Okay, and last but not least, B, inverse secant. Okay, it's positive, so we are in the first quadrant. Inverse secant is the reciprocal of inverse cosine. So that means that it is secant, hypotenuse over adjacent. We are looking for theta. We already found theta. It's in the first quadrant. We actually don't need to figure out what the additional leg of the triangle is because it's just going to be adjacent over hypotenuse. Yay, we made it through. Nice job, guys. Okay, practice, 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 please. Examples 1, 2, and 3, I think you'll be fine with. Watch out for cotangent. Okay, and then with the graphs, you just need practice. So please practice. Give yourself that chance.